All right, so today I think did I hear something? One moment. Oh, I have two. How delightful! Excellence. As a fraction of the class, y'all's are beating out my Math 118 course, but that's kind of easy to do when there's six of you and 18 of them. So, anyhow, let's see here. Let's see here. Let's see. Okay, so the thought there are a couple thoughts that are floating through my head about what I ought to do today, and so I think today, I do recall that simple machines were part of the curriculum when I was in grade school, and I think that now would be a good time to talk about said simple machines. I don't see them in the textbook, and I think they probably ought to be there. Um, Simple machines. Um, there's a particular reason why I would like you to cover simple machines, other than that they're probably in your curriculum if you're going to teach their stuff. Um, the other reason that's going to my mind about talking about simple machines is that on Friday we will be discussing, among other things, at least how to build a good mousetrap car. And so I suppose mousetrap cars are a variation on simple machines, and so I think a lecture on simple machines would be a useful thing to be aware of for that discussion. So, simple machines, we shall go. There are six of them, or classically. um, Who's classically? Or no? Renaissance. Okay. Um, that's a guy I don't know. Oh no. Archimedes came up with this, and maybe Heron of Alexandria. Anyhow, so for some notion of classically, there are six of them. My opinion, there's two. The six simple machines, according to the guys who classified them and made them up in the first place, are one, the lever, two, a wheel and axle, wheel and axle. Let's spell it right. No, I cannot. There are wheel and axle. Three, the pulley. Try again. Try that P again. The pulley. These three, I'm going to categorize myself as some notion of lever. The first one is definitely a lever. The next two are rotational continuations to what it is to be a lever. So, category of these guys, that's lever. Four, we have the inclined plane. You can get an in on that. There we are. Inclined plane. Five, the wedge. And six, the screw. These guys, I am going to categorize myself under the title inclined plane. And so, turns out these guys, the wedge is an inclined plane that moves, and the screw is a wedge that moves in a circle. So, as far as I'm concerned, there's two: the lever and the inclined plane. So this makes things a little more interesting here. It makes things a little more difficult to deal with. So what's the point of these guys? The point of a machine is to change the direction of a force, or to I suppose it would be to multiply the force. I suppose no, that's not the best way to put it. To exchange distance for force, or both. It is possible to use these guys to do both of them. Simple machines are one of these. I believe it's called a complex machine. Complex or compound? Let's see here. Self-locking proof, kinetic energy. Come on. Yeah, that's the word. Compound machines is what they use. Or it says what Wikipedia says it is. Compound machine. Okay. So, alright. So compound machine would be several simple machines working together to do both of these particular tasks. Alright. So okay, so what's a lever? A lever, we have a lever that looks like this. So we have an arm here and an arm there, lever arms, and then we have this guy here in the middle is a fulcrum, like so. And so you put a force down here, you put your F1 there, and you put your F2 here. And so it turns out that for a lever there's this thing called torque. Torque is some force times the radius times your distance from wherever it is. So your R there and your R2 there and your R1 over here. Come on, there we go. So that's torque. And so you turn this force here into a force over there with the torques on here. So it turns out these guys are equal to each other. So that F1 R1 is equal to F2 R2. And so then we can say I need a bigger force out of F1, so divide the R1 to the other side. F1 is equal to F2 R2 over R1. And if, as drawn here, R1 is less than R2, this will be greater than F2. So that means that you now have more force coming out the other side of this lever. But you don't have to have your lever looking like this. You can also have your lever looking like this, where you put your F1 here and your F2 there, and your fulcrum goes over there. And of course you can trade these if you were so inclined. So this guy could go there and that guy could go over there. And so people have looked at levers and decided to classify them and so on. And so this would be a class 1 lever, and then if your weight is here and your application is there, that's a class 2, like a wheelbarrow, and you trade them so that your applied force is here and your output force is over here on whatever it is you're trying to do. Then it's a class 3 lever, and nobody really wants to make those because you usually want to do something different. Okay, well, turns out that we want to do some math through these guys, and so we would like to know what is F1 to F2. So as noted, that's R2 over R1. But this is a really important number here. So it turns out that this is actually F2 times our mechanical advantage. So MA is mechanical advantage. If I spell right. Advantage. There we go. Mechanical advantage. And so, mechanical advantage for this lever is R2 over R1. Well, that's what you have if you just have a nice straight rod. But you can also build a lever. Say if you had a wheel in your axle. So you have a force here. And so that'll be your, supply your F1 there. And you can have your R1 there. And then guy can just go around and around and around, applying a force to say, I don't know. Let me draw that a little bigger. Can I draw it bigger? Yeah, maybe a little bigger. There we go. So you can apply, say, an there we are, F1 there, around your R1, all the way to the center here. And then, I don't know exactly what they had in mind for our wheel and axle. Yeah, that looks like a funny version of pulley to me. So, they have not entirely convinced me of what's going on, of making a wheel and axle being distinct from a pulley. So you have an F1 there, and then you can have an F2 coming off of this guy, and then your R2 over here, off the middle here. Or you can have a pulley that basically looks the same, and so you got this, instead of having a wheel like this, you have your mass down this way, in there, and then you have your force that you're pulling with over here, and then so what this does is the primary purpose of a pulley is to redirect your force so that, well, the force is the same, but now you can pull in a way which is more advantageous. So instead of pulling up, which is just you using your arms and your parts to lift up, if you pull down, you can use the same muscles, but now you can also put your mass into pulling down on whatever it is, and so you get better. You have better ability to pull to lift your mass, whatever it is. But yeah, so the point of a pulley, or the wheel and axle here, is that you basically have a continuous lever going across around your. Let's draw a nice straighter line. The point of a pulley and the lever and wheel here is that you have a lever that goes around, that is continuously available around the fulcrum as you rotate the wheel, as you rotate the pulley, or the wheel and axle here. All right. Do we have questions about levers and pulleys and whatnots? Oh well. I take that as a no. No questions at that time. Alrighty. So, instead of a come here. There we go. So we have that, but we can also do an inclined plane. So I have a. Let's try to make it a straighter line. I have a. There we are. There's our floor, and we would like to lift something up some height there, like so. Well, it is possible, in principle, to take your mass and just lift it up straight up and over to here. But now you have to do the full work of that mass. Alternatively, if you have an inclined plane, it's possible to take your mass here and apply a force this way. Well, now you're not. So if lift it up this way, you have to use a full, big, huge bit of mass. But if you use the same force going this way, going in here, you no longer have to lift it straight up. You can lift it. You can go sideways, so we get some friction going this way, and then you're working against friction going this way, and you're also working gravity going this way, but the combination of the two is less than if you had just gone straight up against friction. It would be nice if these guys were on wheels so that you wouldn't have as much friction. But that's the kind of point of the inclined plane here, is that instead of lifting up this way with so if I just hold on, how do I best go about this? Okay, so let me back up a hot minute here. So there is a thing. We'll probably discuss a little bit more. Probably on Friday. Is this thing called work. Work is equal to force times the displacement of something. So as it so happens, the work you put into moving this guy from here up to here is the work of gravity. So the work of gravity is equal to, well, let's F of this force of gravity here, but we're doing over a short distance, so that's an mg is the force of gravity, and we're going to lift it some height up. So here's the work of gravity that you're working against to lift it up to here. Well, it doesn't matter if you go up this way or if you go up this way. What matters is how much is what the amount of work what the power requirements are to do that kind of work. And so if there's no friction here, how about to go about this? Dang it. So in this case, we're doing an F, some force here, and we're going to multiply by H to go up this way. But these guys have, not H, some distance D. All right. So D is longer. So because D is longer going up this way, but we still have to do the same amount of work here. So this also has to be equal to mgh. So now that means that in order to make this work out, so energy is conserved. Work is a kind of energy that has been done. And so the amount of work to lift it up the inclined plane is equal to the amount of work going straight up here. And so we're exchanging the force applied to do that, this force here for this one here, by making it go further with our distance here instead of going straight up. And so because of that, the force required to move it up the inclined plane is less than if you're trying to lift it straight up. Again, so that's the inclined plane if it's just stationary. Whereas a wedge, if we were trying to, if you had a wedge, say we're trying to split some wood. I mean, Wikipedia has a nice diagram of this. We got a block of wood, and I want to split it. So, you take your axe. Oh, look at that! It's an inclined plane, right? As it goes into here, you're going to split it with this inclined plane. That's a wedge. So the wedge is an inclined plane that is moving, whereas the inclined plane that's stationary is just the inclined plane. And then, well, we also have, say, well, we got this nail here, but I don't want it to come back out. And so I would like it to not just use friction, but I would like to get it into the wood. So instead of just putting it straight in there, we can put, say, an inclined plane around the screw here. And so now the screw is just a wedge that's being rotated into whatever it is that we're into a workpiece. If something we needed to do. Right. So back to my thoughts on mechanical advantage. So mechanical advantage is we have F1 over F2, and that is equal to, at least for these guys here, that'll be equal to R2 over R1. So this is our mechanical advantage. How much more do we get out? This much more. Which means that if this was less than 1, I would be inclined to call it mechanical disadvantage. But that might be what you're looking for. You might be looking for the case where so if you have a car engine, right? Your car engine is doing, at least my car engine will do several thousand RPM, right? Yeah. Several thousand RPM, going from here to there, whatever it is. But my wheels, they're not doing several thousand RPM. They're probably hundreds of RPM. And so you don't want to have, you don't want to be turning that thousands of RPM into you want to turn that thousands of RPM into hundreds of RPM. And so that's actually a mechanical disadvantage, which means that you're actually going to so you're going to go you're going to have fewer rotations, but you're going to have more torque going out of your tires because of all the because the drivetrain was turning thousands of RPMs into hundreds of RPMs. What else we got? But yeah, so the thing about these simple machines, ideal simple machines, the energy that goes into them, which means the power that goes into them, is going to be equal to the work and power that comes out the other side. I think that's the important bits of the simple machines. Anything else that I need to think about here? I think that's that's most of simple machines. Time is that. So I've been yammering for 25 minutes. But I also only have one student here. This year. You know what? If I'm only going to have one student here, listen to me yammer about whatever it is we're doing, I think it would be best to continue other thoughts about work and energy and stuff like that when everybody is present. So let's just say that this is a supplemental lecture about simple machines, which are going to be useful to us. I think that's most of what is actually useful for a simple machine. So I will see you on Friday, and everyone else can watch this at their own leisure. How's that for an idea? Yep.